Symmetry with respect to an axis. The graph of an equation is symmetric with respect to the y-axis if the replacement of x with negative x results in an equivalent equation. The graph of an equation is symmetric with respect to the x-axis if the replacement of y with negative y results in an equivalent equation. Example 3, let's test for symmetry with respect to the x-axis and the y-axis. So we'll start by replacing x with negative x, and we'll see if we get the same equation back. Y is equal to negative x squared. Again, when I do substitution, make sure you use parentheses. Y is equal to negative x squared is x squared plus 4. And these two are exactly the same, so we know we have symmetry about the y-axis. There's symmetry about the y-axis. Let's check symmetry now to the x-axis. Let's replace y with negative y, and we'll see if we get the same equation back. Negative y, I am substituting it for this y, is equal to x squared plus 4. These two equations are not the same, and so there is no symmetry about the x-axis. You can see from the graph we do have a symmetry about the y-axis, but there is no reflection across the x-axis. Let's test for symmetry with respect to the x-axis and the y-axis. We'll start by looking at the y-axis. Let's test for symmetry with respect to the x-axis and y-axis. We'll start by looking at the symmetry for the x-axis first. So let's replace y with negative y. X is equal to negative y squared minus 3. X is now equal to y squared, since this becomes positive, y squared minus 3. These two are exactly the same. Since these two equations are the same, we know we have symmetry, and that is with the x-axis. Let's check symmetry with the y-axis now. We're going to replace x with negative x. Well, negative x equals y squared minus 3. There's no way I can simplify this so it's equivalent to this. These are not the same. So, we do not have symmetry for the y-axis. We do not have symmetry for the y-axis. Here is the graph for x equals y squared minus 3. And you can clearly see that we do have symmetry about the x-axis. It's a mirror reflection, but no symmetry about the y-axis. If you want to graph these on a computer, go to desmos.com. It's a really good website to graph these functions. Desmos.com. Let's test for symmetry with respect to the x-axis and y-axis. We'll start by testing symmetry for the x-axis. We replace the y with negative y. X squared plus negative y quantity squared is equal to 16. X squared plus y squared equals 16. This yields the same equation as we started off with. So yes, we do have symmetry about the x-axis. We do have symmetry about the x-axis. To test symmetry for the y-axis, let's replace x with negative x. We're going to replace x with negative x. Negative x squared plus y squared equals 16. And x squared plus y squared equals 16. This is exactly the same as the original problem again. So we do have symmetry. We have symmetry for both x and y axes. Let's look at the graph of x squared plus y squared equals 16, and it is a circle with a radius of 4. I can rewrite this as x squared plus y squared equals 4 squared, and the center is at the origin with a radius of 4. Now, we notice that yes, it is symmetric about the y-axis, and it is also symmetric about the x-axis. It's a mirror reflection for both the x and y axes. Test for symmetry with respect to the x-axis and the y-axis. In this example, we will start with the x-axis first. In order to test that, we have to replace the y with negative y and check to see if we get an equivalent equation. 2x minus y equals 4. There's no way I can simplify this. So we do not have symmetry about the x-axis. Note, symmetric about the x-axis. Let's check symmetry about the y-axis now. We are going to replace the x with negative x. Replace x with negative x. 2 times negative x plus y equals 4. This results in negative 2x plus y equals 4. And this is not the same again. So there is no symmetry about the y-axis. There's no symmetry about the y-axis as well. Let's look at the graph for 2x plus y equals 4. Again, you could go to desmos.com if you want to check these graphs out. And here is our graph. Notice that there is no reflection across the x-axis and there is no reflection across the y-axis. There's no symmetry at all. Symmetry with respect to the origin. The graph of an equation is symmetric with respect to the origin if you replace x with negative x and y with negative y, you get an equivalent equation. Is this graph symmetric with respect to the origin? In order to check for symmetry with the origin, we have to replace x with negative x and replace y with negative y. And if we get the same equation, it must be symmetric about the origin. So let's try it out. We'll substitute negative x for x and negative y for y, and we'll try to simplify this. Negative x squared is x squared. Negative y squared is y squared. And it looks like we get the same equation as we did earlier. So yes, it is symmetric with the origin. It's symmetric with respect to the origin. Is this graph symmetric with the origin? We'll have to check by replacing x with negative x and replacing y with negative y. Negative y equals negative x cubed. And again, I'm careful with the parentheses just in case it changes the sign. Negative y equals, well, negative x cubed is not going to change the sign because this is an odd number. So we're not going to change the sign. And it's going to be negative x cubed. But this is negative and that is negative. So I could divide both sides by negative 1. And we get y equals x cubed. And that is the same as the original problem, so we know it is symmetric about the origin also. It is symmetric about the origin. Let's go over some important concepts of symmetry. A graph is symmetric with both x and y axis is automatically symmetric with the origin. A graph symmetric with respect to the origin need not be symmetric with respect to either axis. Of the three types of symmetry with respect to the x-axis, the y-axis, and the origin, a graph possessing any two types must also exhibit the third type of symmetry. A graph symmetric with respect to the x-axis does not represent a function.